Okay, ladies, I'm going to give you some notes on section 4.1, so we can try to get caught back up on the syllabus. 4.1, maxes and mins, also known as extreme values, also known as extrema. Sounds like a disease. Extrema, okay? So we have two different kinds of extreme values. We have relative extrema, which are higher or lower than any nearby point. That's not a formal definition. The formal definition is more complicated than that, but that's good enough, okay? And then we have absolute extrema, which is the highest or lowest on the entire graph, on the entire function or entire graph. So let's start by taking a look at this. We're going to take a look at this graphically first. So I'm going to give you just a couple of sketches like this. And this particular graph has endpoints on it. So what we have here is an absolute min. There is nothing lower. And up here we have an absolute max. There is nothing higher. This point right here is called a relative max. It's the highest thing in the neighborhood, and this is a relative min, the lowest thing in the neighborhood. That's your simplest situation, okay? This one has no absolute max, and it has no absolute min. It goes up forever and down forever, but it has a relative max, and it has a relative min. Okay, nice little parabola here. This point is both a relative min and an absolute min. It is the lowest point on the graph, and there is no absolute max. It goes up forever, and there's also no relative max. There's no point that's higher than any point in the general vicinity. All right. And let's see, two more. This one with a nice little sharp turn right here. This point would be both a relative max and it's also the absolute max. Okay, and at the end point we have an absolute min here. Sometimes we talk about this as a relative min, but not usually. We don't usually worry about that. If the relative min's at the end point, it's not usually something that we worry about too much. Okay? All right, so there's your basic sample of what absolute and relative maxes and mins might look like. So the first thing we have is an existence theorem, everybody's favorite. Do these extrema absolutely exist or not? Okay, and we're going to start with the definition of a critical number. Now, we use the word critical sort of casually to be important, but in calculus, the word's critical number. This right here, critical number, means something very specific. It doesn't just mean an important number. First of all, the function has to exist at C. It has to exist. And the derivative at C has to either be 0 or undefined. You have to have a point there, in asymptote, all right? If those conditions are met, then we call C a critical number. Okay, other numbers are important, but this is called a critical number. That's the definition. All right? Relative extrema only occur at critical numbers. That's the only place they can happen. Relative extra can only occur at critical numbers. And again, that's leaving off the possibility of a relative max or min at an endpoint. We're just going to treat endpoints a little bit differently. However, but not all critical numbers are relative extra numbers. So if you're looking for relative maxes and mins, we start with critical numbers. Not all critical numbers give us maxes and mins. Okay? So again, a graphic example. Nice little parabola right here. You'll notice that if this is C comma f of C. So right here, f of C exists. There's a point there. F prime of C equals 0. It's flat. Therefore, x equals C is a critical number. Once you turn it as a critical number, then you can determine if it's a max or min. Graphically, we can see the max or min first, but this time we do have a relative max at x equals C. It also happens to be an absolute max, but I'm only going to discuss relatives. Okay, so let's take a look at one where it's not, okay, not a relative max. So here's our point C comma f of C again, and f of C exists. There is a point there, and f prime of C equals 0. The graph right there is flat, but x equals C is not a relative max or min. Let me rephrase that. X equals C is a critical number, but not a relative max or min. Okay, it flattens out, but it does not go back down or go back up again. All right. Another one. All places are not flat. F of C exists. There is a point there. F prime of C is not 0. F prime of C is undefined. One of those places with a sharp turn. Okay? And so x equals C is a critical number, and and you can tell by the graph that we have a relative min at x equals C. And the last example of this, okay, here's my point C, f of C. F of C exists, there's a point there. F prime of C is undefined. This is a vertical tangent line. Okay, therefore, x equals C is a critical number, however, not a relative max or min. So if you're going to have a critical number, if you're going to have a max or a min, you have to have a critical number, all right? But just because you have a critical number does not mean that you're going to have a max or a min. Okay? All right, some more graphic considerations. So nice little, again, sort of parabola, all right? We want to get some language here, all right? What is f of 2? F of 2 is 10, so therefore f of C exists. What is f prime of 2? F prime of 2 is 0. Check. So we have a critical number at x equals 2. And looking at the picture, we can see that this is a max. I want to make sure you got the language right. The relative max is, this is the y value, 10, and it occurs at this is the x value, okay? So if I say, where is it? Where is the max? You'd say it's at 2. What is it? You would say it is 10. If I ask you to identify critical numbers for me from this picture, you would say the critical numbers are x equals 3 and x equals 0. If I say why, you would say because f of 3 exists and f prime of 3 equals 0. Or for here, f of 0 exists, f prime of 0 equals 0. There's your justification for critical numbers. And again, the language. If I said, well, describe the relative maxes and mins to me, you would say there's a relative max at, the relative max is 4, and it occurs at 3. The relative min is -5, and it occurs at 0. Where is it? Translates into x. What is it? Translates into y. Okay, this one's a little wonky. So looking at a graph, can you identify critical numbers, relative maxes, relative mins, absolute maxes, absolute mins, and sometimes you need to justify that. So first of all, critical numbers, any place that f of c exists, and f prime of c is either 0 or undefined. So that occurs at 2 places. The 2 flat places on the graph here and here. So my critical numbers are x equals 3 and x equals 10. Those are my critical numbers. Okay. If I asked you about relative extrema, you would be able to look at them and say, well, the only place I might have relative extrema are either at 3 or 10. Those are the only 2 places. And at 10, I have a relative min. Okay, the relative min is -4, occurs at 10. You could also say that that's an absolute min, because nothing goes any lower. There are no relative maxes that are not endpoints. As I said, we don't generally talk about relative extrema as endpoints. I suppose you could call that end a relative max. It's the highest thing around, but it's not generally done. I don't think they do it in the back of your textbook. However, we would say that the absolute max, the highest thing that absolutely occurs, is right there. The absolute max is 6, and it occurs at 12. Okay? So at this point, you should be able to do, from your homework, page 207, 1 through 10. I'm going to pause for just a second. Just saying if I can find this. I'm going to pause for just a second, and I'll be right back. Okay, I'm going to give you just a few more notes and get you started on the homework. It's listed in your syllabus, but not have you do quite all of it tonight. We'll catch up over the course of the next 2 or 3 days to get everything back on track. So the next thing we're going to do is find the critical numbers analytically. Without a graph. Finding the critical numbers analytically. So I'm going to give you some steps here that you need to consider. First of all, make sure you know the domain. Remember that the critical number cannot exist if the function doesn't exist. So for example, while vertical asymptotes are very important places on the graph, they're not considered critical numbers. That is a specific definition. Okay, note the domain. Second, find f prime. Right? And third, determine if or when f prime equals 0 and or f prime is undefined. And as long as they are in the domain, those are going to be your critical numbers. So let's just run through 2 or 3 examples of this, and then we'll stop. All right, so the first one, nice little polynomial. We always start with nice little polynomials. Whoa. Okay, so there's your problem. And you need to always, when you're working with functions, pay attention to domain. So this is a polynomial, the domain is all reals. F of c exists for every single value. The next thing you're going to do is take the derivative. After you take the derivative, you need to break this into 2 things. F prime of x is equal to 0. I'm going to go ahead and factor that. And I get 2 places. Okay, and then always consider this. I know for polynomials, you know it doesn't happen, but if you start skipping the step, you're likely to skip it when you need it. So, what are my critical numbers? Critical numbers are x equals 0, x equals 1, because f of 0 exists, f of 1 exists, they're in the domain, and f prime of 0 equals 0, and f prime of 1 equals 0. So they are critical numbers. So all you have to do is find the critical numbers. This means that they might be, it is possible, not guaranteed, but possible, that there is a relative max or min at these 2 values. Not guaranteed. We'll get to that next. Okay. Right now we're just identifying the candidates. Okay. Identifying the candidates. All right. Next one. Little sun on the screen. Okay, so a reminder of what this means. This means the cube root of x squared. All right, cube roots do not have any domain issues. So our domain here is, again, all real numbers. Don't have to worry about anything there. The next thing we have to do is take the derivative. Some of us have to worry about this one more than others. You can either put it in cube root notation here, okay, or leave it in fraction exponent, rational exponent form. When it's time to set it equal to 0, you're going to want it in its nice factor form, so I'm just going to go ahead and do that. Get common denominators. And you don't have to do both of these, do whichever one. Oh, that looks like a 1/2, that's a 1/3. Whichever one you prefer is fine, doesn't make any difference to me. I would say I have a slight preference for this one, but I've been known to use the other one just because I feel like it sometimes. Okay? All right, so we've checked the domain, we've taken our derivative, and hopefully not made a mistake in that process. And then the next thing is to determine if g prime of x is ever equal to 0. So when you've got a fraction, when it's in this nice factored form, you can just take the numerator, set it equal to 0, add 2, divide by 2, and then cube both sides. And so we have our first critical number, x equals 1 is a critical number because f of 1 exists, and g of 1 exists, and g prime of 1 is 0. Then you're going to check and see if g prime of x is ever undefined. So if it's, again, in this nice factored form, You just take the denominator, set it equal to 0. So g prime is undefined at 0. Going back and checking our domain, g of 0 exists. There's a point there, and the slope is undefined. So our two critical numbers are x equals 1, x equals 0. They are candidates for relative maxes and mins. Maybe they're the only places they can happen. We don't know for sure if they happen or not. All right, last example. Okay, so this is a rational function, and the first thing that you're going to note is that t cannot equal 1. All right, so we have a domain restriction, and you might note that there's vertical asymptote at t equals 1. This means that 1, no matter what happens, t equals 1 is not a critical number. It's a vertical asymptote. So there's no max there, there's no min there, there's a vertical asymptote there. So that's something to keep straight, separate from what critical numbers are. All right, I've taken the derivative, and I've left out all the work. You're going to just have to trust me that this is the derivative. Okay? So there it is. And after we take the derivative, the next thing is to look at whether the derivative ever equals 0. Does negative 1 ever equal 0? No. So there's no critical number here. And then we're going to look at whether the derivative is undefined. So we're going to take the denominator is equal to 0. And we're going to get t equals 1. And again, just watching out, t equals 1 is not a critical number. While it is true that h prime of 1 is undefined, h of 1 does not exist. There's no point there. It's a vertical asymptote. So because of this right here, t equals 1 is not considered a critical number. Now what this tells you is that there's no place on this graph that might be a max or that might be a min, might be a relative max or might be a relative min. Okay, so from here, check your syllabus. You can also do on page 207, 11 through 19 odd, and 18 and 20. Okay, I have a note that says to use your calculator for arithmetic if you need to, make it go a little bit faster for arithmetic, but don't graph it. The whole point about this is can you get these answers without physically looking at the graph? Okay, so on your syllabus, it has more problems than that for tonight, but you can stop right here. I'll send you an email on that as well. And then over the course of the next couple of days, you will get caught back up on our syllabus. It may take us a couple of days. All right, happy calculating.